All right, let's get started. So today we are going to continue our discussion on what is about performance, and we have been talking about how to evaluate it. We have been talking about what affects performance, and now, sometimes a lot of things affect performance, but how do we know what's the right thing to do? So that's actually pretty important. But before we start, it's always important to put ourselves back on the same page. So the most important big picture is that all machines that we are using today are so-called monumental architecture in a way that our machine always contains three main parts of the components: processor, memory, and storage. And whenever you have a program, we have to load it into the memory. And once we have that ready in a memory, in your processor, there is a special hardware register called program counter, which would tell us where in the memory should I get that instruction from. And then an instruction fetch unit in your processor would interact with the memory to get that instruction inside the processor, and then the processor can parse what the instruction wants us to do and drive the corresponding ALU to perform operations. And if you have an instruction that needs to access memory, then that's when you are going to have another memory accesses. And when you are done with an execution of the instruction, you will typically change your program counter, either it's going forward or jump to another location, depending on what type of instruction it is to continue execution. And the good thing about this architecture is that, as you can imagine, if I give the machine a totally different set of instructions, the machine can perform completely different without reconfiguring your hardware at all. So that's the good thing about volume architecture, and that's why it's so popular. In the last lecture, we talked about, as a programmer, although we don't manufacture those hardware, we don't design those hardware, there are a lot of we can do to better utilize the hardware. So for example, when we compose our algorithm, sometimes we just implement the pseudocode without considering what the processor is going to do with the compiler, and the processor is going to do with those operations. And if you don't have any knowledge about computer architecture, you can easily just use the pseudocode, right, the right-hand side of code, which has worse CPI, give you very bad performance. On the other hand, sometimes we write programs just based on computational complexity. We think we don't need to do additional stuff because the later algorithm is good enough to help us solve the problem. However, sometimes it's not about the easiest way or the fewest amount of lines to achieve your solution. It's more about how can I make this solution being done efficiently. So this example tells you, even though before this main loop, if we could have add a sorting to change the data alignment, it would make the behavior of this following loop even better on your processor. Oh, even though the number of total operations of this loop is unchanged before and after adding the sort. However, it will make the loop going faster. And there is a reason for that, which we will tell after you take the midterm. However, these two examples already tell you how powerful a programmer knowing the computer architecture can be really make a difference on the application performance. A lot of people, they have the myth. They feel like, okay, I don't have to be a good programmer because we have good compilers. However, through the last lecture, we had the demo. Even the best compiler, there is no way for the compiler to transform a poorly written code into a perfectly written code. And there is a reason for that, because the compiler optimization, its ultimate guideline is that we don't want to get things wrong. So they don't want to bear the risk of any change that could potentially render your algorithm to have a different result from what the original intention of the programmer. So it can only perform very conservative optimization to not get the result wrong. So if you don't describe your program, your problem solution in a way that the compiler easy to optimize, there is no way the compiler can very aggressively rewrite the whole thing for you. So that's why another reason, even though the compiler right now is very mature, we have a lot of researchers doing compiler optimizations, we still need to be a good programmer because there are things that compiler can never do because of the conservative nature that compiler has to take. So hopefully this would give you sufficient amount of reasons why you need to stay in this class. And as an icebreaker of this lecture, I want you to remind yourself and discuss with your friends regarding what's the right thing you have ever done in your life that you think, well, this is the best decision I have ever made. Why and what is that and why is that? All right, what do you guys think? Tell me something that you thought you have done the right thing in your life, and why is that? And how do you make that decision? Anyone would like to share? Part of yours. Okay, Mitchell, what do you think?
Okay, this is very specific, but I think this was for a skill assessment for one of my CS class.
Mm-hmm.
And then I think I was on this skill assessment was like on the line of getting an A,
Mm-hmm.
between an A and a B. So I was doing everything right, but except for like one problem, I couldn't get this problem right because of like some specific command lines I had to do.
Mm-hmm.
So what it did was like, okay, I just had to like print out the list. I'll just brute force it by just typing each list out because the list was pretty short.
Uh-huh.
And then yeah, I passed that skill assessment, got an A.
Okay. So it means that, well, so that's the right decision because you found the easiest way to get through it. But how did you make that decision? Like, why do you think you should do that?
Because I tried everything that I can, doing it the right way. And when I was about to give up, I said, all right, maybe sometimes you got to do things the wrong way
Okay.
to get started.
Okay. What else? So that's a right decision because you can ace it, right? And with low cost, right? Nothing to lose, right? What else? Come on, everyone must have a successful story in the past, right? Am I making all the question too philosophical? Sort of. Judy, do you have one?
I mean, I shared that like buying certain things that
Mm.
interest me from like my hobbies or like my interests, like I usually don't regret it. Like getting a great PC setup, for example, I use it like every single day, always.
Okay, so why do you think you don't regret it?
I don't regret it because every day I use it.
Because you use it a lot. It's a big part of your life, right? And so if there is something that can optimize a big part of your life, that's a great decision, right? What else? Okay, so maybe this is a very deep thought question that remind yourself, what are the right things that I have done? Maybe broke up with my previous relationship, right? So something like that, right? So there are a lot of things that you probably already have in mind, no matter it's good. Oh, okay, what's yours?
Oh no, I was going to ask you if you have an answer to this, like yourself.
Oh, do I have an answer of myself?
Yeah.
Huh. Yeah, break up with my ex. That's probably the right decision. Yeah, it makes okay. I can tell you, like, no. So I want to share. That's really a good decision. Although I shouldn't comment on that, but there was one period of time I was very suffering. We were in a long distance, and at the time I was sick, but my ex still wants to like break up with me, and my feeling is like, should I continue doing this or should I let it go? And during this period of time, like I think she keeps hurting me in a way that like because like I grew up in a single parent family, and like she's like, well, it's very unbelievable that she said that. She's like saying that, oh, for I don't know if someone grow up in an environment like you would give me happiness. Wow, right? So, and I was trying to like persuade that, I could I could be a good guy, right? Like give me some more chances. But at the same time, I was in a very bad code and no one is taking care of me. So I was like every time when we have the phone call, my feeling is like, okay, don't worry. And then, I try to persuade, but in the meantime, I'm also suffering, right? And there's one day, it's actually the last day of the year. Like she said it again, and I said, well, okay, whatever you want, whatever, right? Surprisingly, the next day when I wake up, I'm fully healed. Like it, like before that day, every day was raining. And when I wake up the day after we broke up, I look at outside. Well, it's sunny outside. It's the first day of the new year, and the next day I fly. I have a ticket to Japan, and I was super happy with my trip. I went to all the temples with new wishes, and I feel like my life was brand new after that. So that was my experience, and I think that's the right decision I made. All right, so outline. So today we are going to talk about the definition of speed up and regarding Amdahl's law and its implications. So we talk about like quantitative analysis of performance. And as an engineer, it's really important that when we talk about something, we can always give people with citations on numbers or some kind of quantitative measurement instead of just a feeling, right? So sometimes we do have a lot, like for me, like yeah, as you guys can see, I'm like an INTJ person, right? Like I'm more a J person, so I want to see the real number. I want things to be well planned instead of just give a feeling, right? So I'm sure my ex is a P, so there are a lot of difference here. So the thing here is that you want to give a quantitative analysis or definition of what is better and how better it is instead of I feel this is better. Why? Because I feel it's better, right? In a lot of cases, a lot of disagreement come from that. So here in computer architecture, if you have done a reading, you know we have a definition regarding what is better, right? So today, the first question, I want you to remind yourself regarding what you have learned from the book. How do we define the quantitative assessment of better? All right, let's see. What do you guys have in mind? So, well, I like this distribution. It's kind of like a normal distribution. So a lot of you might be guessing. So why don't we just like discuss with each other and put everybody on the same page? Maybe you just miss one concept or one number. Go.
Amount that portion gets split up. Like in proportion to making our way the amount gets split up goes like along with how much of it takes, I guess. So then so then the equation is this 1 over 1 minus alpha. 1 minus alpha is 1.8 plus alpha, which is 0.2, right? 2 divided by k. K is going to be the amount it gets sped up by. So then I guess this cancels. Oh yeah, because he was putting the 20% of that data in the video, so everything else stays the same. Oh. Yeah. How much faster is y than x? So let's see. Y is going to take. Oh wait, actually, let's see. There is a change. Yeah, because I think that the CPS. Oh yeah. Oh, I see, I see, I see. Oh, I get what you're saying. Yeah, 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 yeah. So actually the typing instructions can change. Yeah, maybe the typing instructions can change. Everything else is. Yeah, yeah, yeah.
All right. So after discussion, let's review what you guys think now. Okay, so more of you think the answer is D. There are still quite a few think the answer is C. So for this type of question, first of all, we have to put everybody on the same page. What does that mean by speed up? What is speed up? Okay, Mitchell. Okay, old execution time over the new execution time, right? So that's the only definition of speed up in computer architecture. So this is how we compare, right? The old execution time, or say the execution time of your baseline program, the execution time of your unmodified program over the new execution time, the optimized execution time. So that's our definition of speed up. And this is very important, right? Because we have to know like how to compare, right? Quantitatively, right? Because without that, right, there is no standard of comparison. Agree? So that's our comparison, right? So here's the definition of speed up, saying that in this formula, we consider x as the unoptimized and y is the optimized, right? So the execution time x over the execution time y is the speed up, right? So for this question, what's the older execution time? If you are familiar, if you remember what we have done, we consistently work on this set of numbers, right? That's the performance equation on the first day, right? So this one is 2.5 seconds. And if for the new one, right, if you use the same formula, the only thing that would change is the IPC and the cycle time, right? And then you will figure out it's 2 seconds. And if you do the math, 2.5 over 2, that's 1.25, right? So that's the only definition of speed up for this for this question. So the very first takeaway, the definition of speed up of x over y, y over x is execution time of x over execution time y. So that's the definition of speed up. Okay, so you might think about why we start with that. So now we are going to talk about another one, which is very important, called Amdahl's law. So a lot of you were asking me if cheat sheet is allowed in this class. I would say in fact, there aren't that many equations for you to memorize. And the ones that you need to memorize, they are really important. So I won't allow you guys to bring cheat sheets. But and also seems like another law, but let me tell you, it's basically nothing new. So let's do this. So first of all, Amdahl is invented by this guy called Gene Amdahl, and he was born in 1922 and passed away around 10 years ago. And he is one of the designers of IBM 360 and 704. I don't know what kind of machines they are, but based on the picture, this is the 704. So it's a so this is not an office. Like this whole thing is a computer, and you have to operate the computer here, right? So this is a big computer back to the days when Gene Amdahl was engineer for that machine. And later on, he has designed one of the machine called Amdahl 470 V6, and where his company called Amdahl's Corporation, later on acquired by Fujitsu, has that machine. So for this machine, so again, the machine itself is not this one. It's this one plus this and this. So that was the good old days. Your machine is really big like that, right? So and in the past, this kind of machine, they probably need tens of thousands to purchase, which is very expensive even from today's perspective, right? And think about it was like 50 years ago, right? So that's more like, so you can consider the inflation during these days, right? Even in the past few years, that was crazy, right? So it was a really expensive machine at that time. And he is the founder of that corporation. He earned a lot of money. So he started his career initially as an engineer and later on become an entrepreneur. And when people become an entrepreneur, they would learn a lot of different ways of selling things. But that's before we talk about how he sell Amdahl, let's talk about what is Amdahl. So the definition, the Amdahl is basically saying that the speed up is defined in this way. So it's 1 over 1 minus f plus f divided by s. So what's the f here? The f is the fraction of time in the original program, the baseline program that we can optimize. And s is the speed up that we can achieve on this f fraction of time. So that's the definition of Amdahl's law. All right, so you might be confusing now, right? Because just a few minutes ago, from my mouth, I just say that there is only one definition called speed up in computer architecture: execution time baseline over the execution time optimized. That's the only definition. I keep saying that's the only definition of speed up. Now this guy gives me a different equation. Why is that? So I want to tell you, sometimes don't buy in an idea from a businessman too easy. Because if you investigate what is Amdahl, let me graphically tell you. So first of all, Amdahl is rescaling the baseline execution time as 1. So now consider your program consists of 2 parts. One part is f, this fraction of time that an optimization can apply on. By optimization, it could be like, for example, I want to optimize an algorithm, and this is the amount of time that algorithm that I'm targeting that takes. And 1 minus f, right? If this is the optimizable part, this is the not optimizable part, right? So that's 1 minus f, right? And since you can only speed up this part, after you speed up this F part, the amount of time that the F part will take is what? F divided by S, right? And 1 minus F, since we cannot optimize it, so it remains the same, right? So this is the baseline. This is the enhanced. Use the speed up equation. What did you get? Isn't that Amdahl's law? So I was not lying, right? This is still the only definition of speed up. And Amdahl's law essentially is just realigning or say rescaling your baseline execution time into 1. So just by doing this, you will automatically get Amdahl's law. Right? So this is not a new equation. This is just a, I would say, like revamped version or another way of selling the concept of speed up equation. Isn't that something a lot of companies would do, like rebranding RTX 4090 as RTX 5000 something, right? I didn't say which company, right? But sometimes, right, you see that's what they do. Okay, so you might think about, okay, since this is just a rebranding of speed up equation, why do we want to talk about that? And sometimes you do want to agree the way of the rebranded equation does give us more insights from its original forms. So now I'm going to give you a few practice to see what are the implications after reformatting speed up as Amdahl's law. So I don't know how many of you are gamers, like how many of you recognize this game? What is that? Final Fantasy, right? So like Final Fantasy used to be a very legendary RPG games. Like that's probably one of the main reasons people buy game consoles, right? And when I was a kid, I really liked to play games, but like I found, well, this is very sad. I feel like I keep telling you guys sad story. So if you are enthusiastic about gaming, right, try to do it as much as possible as long as it's not affecting your GPA. Because all my friends, we were gamers, but after we start working, we are playing a different game. It's calling the game of buying games. So it's kind of interesting because I have a group of good friends when I work at Google. We all love this like 2D stuff, like animations, comics, games. And our conversation typically starts like, oh, I purchased the game on Steam yesterday. I purchased the game from the online store yesterday. Oh, have you played it? No, I don't have time to play it. I don't even have time to play whatever game I bought last month. So typically like, yeah, so there was once like a friend of mine visited me in my office at UC Riverside, and he saw that, oh, I have a box of Pokemon games, and he's like, oh, are you playing Pokemon games still? I said, well, no, I just purchased it and put it right there. And he said, do you mind if I take it and play it? And I say, sure, because like I don't have time doing that, right? But yeah, so today I'm doing some search on what's going on is the recent involvement of Final Fantasy, and I found, oh, for the same one, they really make it like a pocket version, which is a low resolution one, but work for your iPhone. But anyway, okay, why we are talking about that? Because Final Fantasy is notoriously bad for every time when you go into a different section of the game, you have to load the map. So let's see what can we do with the map. All right, let's take a look. Okay, the initial vote shows like 58% of you think it's C. It also means there are 42% of you don't agree. The answer is C. So why don't you guys synchronize with others regarding what you guys think is the right answer for this one. All right, let's take a look. What do you guys have in mind after discussion? So here we got, okay, now 93% of you think the answer is C. So can I have someone just let us know what you guys synchronize, what's after you guys synchronized? Okay, Corey, do you want to give it a shot?
For how I got my answer.
Yeah, since you got my $20, right?
Yeah, no, I just plugged it into the speed up equation.
Uh-huh.
So,
Which speed up equation?
the one that you gave us on the previous slide. I mean, they're all the same, but I just used that version.
Okay, so but would you mind to use Amdahl's law for that?
Yeah. The 1 over 1 minus.
Yeah. Okay, how does it work?
Yeah. So I just plugged it into 1 over, and then like 1 minus alpha, which is 0.05, yeah, and then plus 0.95 over 100. Yeah, like that.
Okay, so this is how we get it, right? So the F means the part that we can optimize. And in this case, the solid state drive or the flash drive is optimizing the HDD, which is the hardest drive part. And so 95% of the time could be optimized, and by a factor of 100. So using that equation, it's not too difficult for us to get 17 times. But isn't that surprising to you, right? So sometimes people advertise you that, okay, we can get you 100 times faster compared against hard disk drive from the businessman's perspective, right? But if you are smart enough, you know how to use Amdahl's law, and then you will figure out, although yes, it's indeed 100 times faster than a hard disk drive, but it doesn't translate to the whole application. Even though here it sounds like 95% is the majority of time, but it only gives you only 17 times speed up, which is far away from the 100 times speed up, right? Okay, question? Can we get a calculator? What? They give calculators? Okay. Does that answer your question? Okay, awesome. Okay, so here's the thing, right? So for Amdahl's law, this is how we learned. Now, right? The one of the first thing you learn is that, okay, don't be fooled by businessman's slogan, right? Sometimes 100 times doesn't really translate to the real speed up. You really need Amdahl's law to give it a shot. So now, I wanted to ask you a question. So for this question, can you see how much faster if given we already have solid state drive, and if you are working for a company for solid state drive, how are we going to achieve? How significant do we need to do to achieve twice speed up? All right, so let's see, what do you guys think? So most of you, well, so this is like a later shape. So why don't you guys discuss with each other regarding what you guys have in mind? Oops, sorry.
Oh, then it's not possible. Yeah, even if you completely cut the 60%. Yeah. Oh yeah.
Oh, so like the
Yeah, because the limits of the speed up is 1/1
okay.
which is I think it's like 1.2. So it's almost the same, actually, 2 times.
All right, let's wrap up. All right, after discussion, ta-da. Okay, most of you think the answer is E. So, can some of you telling me why? Okay. Oh, you got a question? We are looking for S.
Oh yeah.
Yeah.
Oh okay. Yeah. Then we are given the speed of time.
Mm-hmm.
It comes just come out anyway.
Right. So here's the thing, right? Speed up. If it's larger than 1, it means that we are making it faster. But here, if you try to solve the S or say X, whatever, you will figure out that it's a number smaller than 1. So it doesn't make sense at all, right? So it means that the whole thing doesn't make sense, right? So, sometimes, a lot of managers or boss, they are not reasonable, right? For example, if today you work for a game console company and your boss asks you, hey, can you design a new storage device for our game console to make the map loading twice faster than what it is now? And if you know Amdahl's law, your very first thing to do is not looking for the new memory technology or even invent like a Nobel Prize memory technology. You should prepare your CV and look for a new job, because you are given a mission impossible, and basically your boss is asked you to leave, right? So if you know Amdahl's law, you can read the air, right? It's implying you like, no, I'm giving you time to leave, right? Don't let me fire you, right? Do it yourself. So here's the thing, right? So this doesn't make sense. However, this also gives us another insight that you can get from Amdahl's law, is that there is a maximum boundary of speed up. So, and this is easy to get if you know Amdahl's law. So the maximum speed up you can get from anything that is infinity, right? So if I replace the infinity with the speed up factor, then in f over infinity, as many of you know, that would give us a 0, right? So you will get 1 over 1 minus f. So if you use 1 over 1 minus f to do a quick check, you'll figure out, for this perspective, 1 over 1 minus f, no matter how hard I worked, I can only get at most this amount of speed up. So someone saying that twice speed up, that should be easy for you. No, that's never possible, right? So here's the thing. This is an important perspective for a lot of engineers or a lot of managers to know, that you have to first know where my limitation is, right? So in fact, this would save a lot of efforts in developing, like not to develop useless products. So one of the products that I want to talk about here is the Intel Optane memory. So Intel Optane SSD is a 3D crosspoint based technology, and they are guaranteed a latency that is 8 times better than the solid state drive, right? So if you don't know anything about application performance, and as a consumer's perspective, you will hear like, oh wow, so I can actually make my SSDs like 8 times faster. And for people who play like Final Fantasy, you feel like, yeah, that's probably necessary for me, right? However, now, as you learn from Amdahl's law, right? Even though you get the best ever storage device, right? The best ever something, right? Like Kim Cook, I like to say that. I believe this year, later, like after the summer session, we will hear, this is the best ever iPhone we ever made. Anyway, but something like that, right? Even though you have the best ever solid state drive, it's only going to give you like 1.2 times speed up. And in fact, in daily use, a lot of people also find that. So this is the booting time for Windows 10. And for hard disk drive like this one, it takes like 60 seconds. But for like Samsung, like flash-based SSD, it's about 22 seconds. And using Intel Optane memory, yeah, it's indeed faster, 20 seconds. But do you care about that 2 seconds? If I told you that you have to pay twice amount of money than this to get this 2 seconds, are you going to do it or not? Right? So here's the final story of Intel's Optane memory, is that this doesn't exist anymore. So what does that mean? Is that probably the manager of the team plus the manager's employee, they all get laid off. Right? So sometimes you might think about, as an engineer, why do I need to know that? Well, if you want to pursue a career like Amdahl at some point, become a businessman or the project leader, you want to know if I could have a future. Right? And in fact, a lot of people, when they go, like, for example, at Google, if you are going to be like an L6, right, you need to lead a team. And sometimes, I want to tell you something interesting I observed at Google. So Google is a very interesting company in a way that a lot of teams, we encourage collaborations and we produce like internal like infrastructure or tool chains. And my feeling is like, when do you know your team is going to be gone or not? It's totally depending on your out degree of your products. What does that mean by out degree? Who uses that? Right? So if one team uses your product, you still have one out degree. So that's why when I work for TF Lite, because we have to compete with JAX or TensorFlow or MediaPipe, this kind of Google internal products. So we have to convince like Android, we have to convince like Pixel team to use our product, right? To keep the significance of us in a company, right? So same thing here. Like you might think about this is not relevant to me, but the thing is that this, like, if no one wants to stock at the level of L4, right? So if you want to go to events, at some point you have to become a project leader. And to keep your state as a project leader not being laid off, you have to show the significance of your team, right? But if you don't have any kind of assessment regarding if this is going to be valuable for everyone, like using Amdahl to at least convince people my stuff is going to be useful for you, you're not going to be a successful project manager. Agree? Right? So that's why we have to learn this. Okay, so now, you know, like it could be more complex. Let's try to use Amdahl's law for more cases. Well, so this question, I believe, is more complicated. So to save our time, why don't you guys like work together on this one?
But we also did it in the previous question. We said the maximum we can speed as a speed part is 1.19. So maybe that's not even right. Maybe it's only
All right, so let's see. Okay, so okay, so why don't I just like show you guys some of the basic concept. So and also no worries, if you can have multiple parts that you can optimize. The most important thing is that again, remember it's the rescaling of the original execution time into several different parts. So find out if I have two optimizations that are disjoint, meaning that they cannot apply on the same part of the code. Then just separate out which part of the code, or by which part of the code, it means like the time, the fraction of the time the first optimization can apply, and the sole time that the second optimization can apply, and the rest, right? And then use Amdahl's law, right? Like how much factor can optimization one speed up the F1, and how much factor that the optimization can speed up the F2. And sometimes, if you're unlucky that optimization one and optimization two, they can apply on some parts together. It's again, you need to figure out different segment of times by expanding the Amdahl's law. And then you can get an expanded format like this. But for this particular question, the reason why I want to want you guys to discuss instead of just do it solely, because it's really like 4 different formulas, right? So the first one, replacing a CPU, the CPU can only contribute to the operating system part, which is 84%. So you can consider now, we are not changing the 16% at all. If you are not changing, the speed up is 1, right? So you will get a speed up of 1.72. A lot of people pick this one, but let's see the remaining. So for the second one, it seems like we replace both processor and the SSD. However, for the majority of the 84% of the time, we can only speed up by 1.2 times, even though for the minority, it speed up by 100 times, which gives us a synthetic effect of 1.43. And for the third option, it gives us a little bit more, because even though it sounds like 1.5 times is smaller than 2 times, because so sometimes, right, it's still beneficial to replace the minority part, or say optimize the minority part, because like if you like numerically measure that, you will figure out that it's still beneficial to do it sometimes if you have the money, right? So, and I bet this is the game that Intel wants to play. They want people to replace both their processor and solid state drive with Intel offering. But the thing is that we are only willing to buy their processor, not their SSDs, right? And the thing is that, consider the price. It only gives you 0.004 more, so it's not worth it, right? So again, right, this calculation, it only gives you the speed up. It doesn't count the money in, right? So a lot of people, when they make decision, they would time the amount of money they have to pay. So I'm sure if we consider the cost effective, the first one is probably still better than the third one, right? But for this question, if you use Amdahl, so the winner is C, but A is also not too far away. So most of you get even answer like A and C. You are not too far away. All right. So, but why we talk about this is because, okay, if there is only one thing that I can do, how to decide what's the one thing right? If today I can only pick, I only have the budget to replace the solid state drive or the CPU, what should I be doing? Then, based on Amdahl's law, it's obviously that we can tell the biggest fraction of the time that we may be optimized would probably be the one that worst investigating. So that goes to a golden rule of computer system design or even software engineering. So Butler, Lampson, and a lot of others who are the pioneers of computer engineering or software engineering talk about make the common case faster. Make the common case faster. So if you can only devote your resource on one thing, the one thing right to do is figure out what's the common case. However, to be more effective, what is the most common case is actually the most time-consuming case. Or in Amdahl's perspective, the part of the code that would consume the largest amount of F in your baseline program. That's the most common case. And that's something, the second corollary, that second insights that we should learn from Amdahl's law is that we want to make the common case fast. Now, how do we identify the most common case? So there are several ways, like use perf, use gprof, and insert timestamps. So here, I'm going to show you a quick demo regarding their outputs. So the first one that I'm going to show is using perf, which is the tool that we will be using in your assignments a lot. So here's a program that we want to profile. This is a program using GPU to do sorting. And without any knowledge of this program, we try to compile this code with -g. And now we are going to use the perf tool. So the usage of perf tool is that you use perf record to record the execution, and it will generate a trace. And when you want to read that trace, because the trace is encoded in a binary format, only the perf program can understand. You have to use the specific command called perf report and with --stdio, which means that you are able to interpret it in a way that the standard output format can understand. And I highly recommend that you should redirect it to a file because it's easy for you to track because the output is really long. So for example, you can use the Unix command called head to see what's the first 20 lines of output. And it will tell you this. Like, okay, for this particular function, it takes the most amount of time. So some of you might be wondering, okay, why it's encoded in this way, right? So here are something that I have to tell you is that sometimes if it's the code that you wrote for yourself, it's easy to profile because it's in the executable and you can add a debugging flag for that. And very likely, if you see a memory address like that, it's more likely some kind of external library that you call. And it's hard to tell sometimes, but very likely this is probably like the system library or some kind of standard library like quicksort that we have in the system. So you can somewhat guess what's happening. However, to be more precise, or another thing that you can do is to use object dump to really see into this assembly code to see what's happening. Another one is that you can use the tool called GNU Profiler, which is gprof in the Linux. To use gprof, you need to compile your code with -pg, profile and debugging. And then when you run your program, you don't have to do anything. You just run it, and then it will generate a profiling file. And then with that, after you get that profiling file, just tell what's the binary I used to run this instance. And then what's the profiling output, and gmom.out is the default one. And it will tell you where we spend most amount of time. And sometimes gprof is better because it will give you more information because for this kind of standard C library, it's also provided by GNU. So they are able to know who they are. And for perf, because it comes from a different perspective, so it's harder for the perf to know that. So as you can see, it tells you 100% of the time we are doing a compare. So which is, and if you remember in quick sort, right, we spend a lot of time doing comparison, which is larger, which is smaller. So you know, okay, if I can find a way to make the comparison faster, I can make the CPU sorting faster. Right, so that's the journey of the profiling tool. So now another thing that I want to tell you, right? And another tool that you can use is that if you are the author of the code, it doesn't hurt to insert some timestamp. So here's the demo that I want to also show you is that a lot of people, when they do code optimization or when they talk about the performance problem, they only do things based on their impression. But in fact, optimization is actually a moving target. So here I'm going to show you the demo in a certain way that I am going to first show you. This is the baseline program where I put my data on the hard disk drive, and then I use an Intel CPU to sort. And with that, we are going to generate a table which you can easily identify based on the timestamp. The total execution time is 17 seconds. And which part is the most time-consuming part? The file input or the CPU kernel? Like we have a total of 17, right? Around 2 seconds in file input and 15 in CPU kernel. Which part is more significant? CPU kernel, right? So based on what we have learned from Amdahl's law, what's the first thing that I should do? Optimize the CPU kernel. Yes, I hear you, right? So now I'm going to use GPU code to accelerate that part. And now, after I accelerate that part, line 1 is the optimized part because I didn't optimize file input, right? So this part remains the same. So that's 1 minus f. However, for the CPU kernel, because I replaced it with GPU kernel, so it's only like 0.91 now. What a magic, right? That's why everybody loves GPU, right? Because I got a speed up of like 16 times, right? However, now, if I need to find out something to work, right? Because for my team to survive, I keep finding problems. What's the new problem? The file input, right? So here's the thing. Sometimes after you optimize your code, the new target changes. A lot of people, they keep thinking about, okay, machine learning is all about matrix multiplication. So we produce a lot of new AI accelerators to accelerate matrix multiplication. But I can tell you right now, matrix multiplication is not the most significant problem. Because most of the time, we are spending more time on memory accesses. So if you could have changed the layout of your data or find a way, new algorithm that make memory access faster, that would be even more efficient than developing new matrix accelerator. But for this case, apparently now file input is more important. So now let's do it again and let's see. So now with solid state drive in play, the file input is only 0.3 seconds. Now the GPU sorting again becomes the most significant. So this story tells us that optimization is a moving target. Every time when you apply a new optimization, you need to revisit Amdahl's law to know what's the new target. Okay, so that's the third. Now, the fourth one, Amdahl's law is getting more important because nowadays we have parallel hardware, meaning that we have multiple processors. So an easy way to estimate the effect of parallel processing is that since most of the parallel processors right now are so-called symmetric or say homogeneous parallelism. So we are assuming we can, if you have n different numbers of processors, then you can speed up that parallelizable part by a factor of n at most. So using the format of Amdahl's law, we can just replace the f optimizable become f parallelizable and a factor of speed up as n. which is the number of your processor. So based on that format, can you have some insights regarding how does that help us in software development in the era of parallelism? Question? It means it can be described as a real number. All right, so B and C. So why don't you guys discuss with each other?
I think each partition does not matter. It just matters how many sheets are connected to it. For I also think make it fair enough. Like a single course performance doesn't matter. But yeah, I guess it wouldn't matter. It's slowly on each
All right, let's take a look. So after discussion, okay, B or C. So at least one of them is correct, right? So, okay, which one? Is the first one, if we have unlimited parallelism, the performance of executing each parallel partition does not matter as long as the performance slowdown on each pieces is bounded. True or false? Yes or no? How to look into this? So remember, right, if we have unlimited parallelism, let's just put the n as infinity, right? So if the slowdown is bounded, okay, put whatever number you like, right? However, because the bottom is infinity, so this part will be 0 anyway, right? So what does that mean? It doesn't matter, right? So that's why I say complexity doesn't mean anything now. Because even though I can increase the complexity, however, it means more if I can parallelize an algorithm, right? So what does that mean is that if we enter an era where we have large enough parallelism, complexity doesn't matter. Now, with unlimited amount of parallel hardware units, single core performance doesn't matter anymore. True or false? Do we still care about the performance of Intel CPUs after we have NVIDIA GPUs? So the answer is, again, look at this formula again. Now, who decides that performance? So first of all, right, if we have a GPU at some point, if all the GPUs has sufficient amount of parallelism, your performance is basically depending on how fast you can execute this F parallelizable part. 1 minus F parallelizable part. Do you agree with that? So that's determined by your CPU, right? So what does that mean is that if one day, okay, let's say NVIDIA can solve all the parallelizable problems, those non-parallelizable part, which the single core processor can only do, the single core processor can only do, will determine your performance. So what does that mean is that the speed up is determined by that. So single core performance still matter. So with unlimited amount of parallel hardware units, as we said, right, because your speed up is determined by 1 minus F. So the fraction of parallel part will determine your speed up, right? So this is true, right? So the other thing, like this part, like the overhead, that's included in the 1 minus F part, right? So what does that mean is that you don't want that to hurt you too much, right? So turns out 2 of them are correct. However, the important implication here is that it matters more for how you can parallelize your program. So one of the bizarre that a lot of you might be thinking about is that in the first day of the demo, we talk about quicksort, we talk about merge sort, which has n log n. Why is it not as competitive as n log square n? So if you take a deep dive of this algorithm, for merge sort, this is the partition of your work, right? So that's how you get n log n. However, if you want to parallelize this task, what can we do? So it turns out, if you want to parallelize it, in the very beginning, I can get the parallelism like n divided by 2. However, to the next level, only n divided by 4. And then later and later on, even worse, right? And at the end, it becomes a sequential algorithm. So the parallelism doesn't help this part. However, if you have Platonic sort, if you check the algorithm better, you will figure out every time the comparison they made is always equal to the amount of half of its elements. Every time it performs parallel comparison of 2 elements. So that's why your parallelism remains the same throughout the whole algorithm. And the more parallel units you have, the faster your application, even though you need more operations per thread. So that's why Platonic sort is faster than quicksort in many cases, right? So it sounds like it needs more operations. However, every time you have more parallelism. So that's why it's faster. So the corollary for it is that if you can build a processor with unlimited parallelism, the complexity doesn't matter at all if your algorithm is parallelizable. So what does that mean is that the future of software algorithm development should be focusing on how to parallelize your algorithm rather than reduce the computational complexity. So that's something CS101 didn't tell you. And that's really important for you to learn in the future. However, if I say this, CS101 teacher is going to yell at me. So I add one more corollary here, is that if you think about the future, if we solve all the parallelizable problems, there are still algorithms that is hard to parallelize. Then single core performance still matters, complexity still matters. So now everyone is happy, right? So here's the takeaway for Amdahl's law is these 5 things. Each optimization has an upper bound. Make a common case fast. Optimization has a moving target. Exploiting more parallelism is more important nowadays. And single core performance still matters. And before you leave the classroom, just don't forget we have a reading quiz due next Monday before the lecture. Assignment due this Sunday. And book your exam slots. Check website for all the resources. And we do record our class. And a discussion session tomorrow will be by the TA. And if you have questions regarding your assignment, it's a good idea to go. Other than that, enjoy the rest of your day. There's no lecture for the lab. I do have an office hour after this lecture. Other than that, I will see you next week.